Okay, so I am going to prove a nice lemma for splitting fields that is going to get us going on some other things. So so let me just talk about this. The extension lemma. Okay. There's a couple extension lemmas. Um, so okay, so let me just say this. So okay, so let's give some setup. Okay, so if let's say sigma from F1 to F2 is an isomorphism. Let's say is a homomorphism of fields. Then so this is like my first thing. Then it extends to a homomorphism of polynomial rings. Homomorph of polynomial rings here. And I'm just going to denote it by the same name. Okay? So in particular, here what we'll do is we take a polynomial a0 plus a1x plus adx to the d, and this polynomial maps to sigma of a1 plus sigma of a0 plus sigma of a1x plus dot 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 plus sigma of adx to the d. So we have this new, so what we can do is you just take the polynomial, apply the sigma to the coefficients. All right. All right. So, and then abusively, we're going to call it the same name. Okay. So now here's the claim. So the claim is so that's what we have. So let me state the theorem. Okay. So let sigma from F1 to F2 be a field isomorphism. That's step one. Let now, first ingredient, second ingredient, let f of x, let's say f1 of x, be equal to some polynomial. ai x to the I is equal to 0 up to d, be a polynomial in here. And so let f2 of x be equal to sigma f1 of x. So it is the polynomial with the coefficients all here, be this, be as described previously. Okay? So let L1 and L2 be splitting fields of F1 and F2, respectively. Okay? So when we're doing splitting fields, we use some algebraic closure to define it. Okay? Or you can do it symbolically, right? By keep adjoining roots and then peeling off a term. Okay? So the claim is that so in this setup, so there exists some tau from L1 to L2 such that the following holds. So we have L1 to, so this is all we're doing. So we have F1, F2. So we have this isomorphism sigma. This goes into here, this goes into here. These are subs, like subfields. And such that this diagram blah commutes. Okay, so this is a theorem. What does it mean for the diagram to commute? It means that, okay, so this means that for all alpha in F1, okay, so it means that, let's call this J1 and J2. It means that J1 of tau of alpha is equal to J2 of sigma of alpha. Okay, so you can go around the diagram in two different ways and you get the same thing. All right, so this isomorphism extends to an isomorphism of splitting fields. That's the point. Okay, so all right, so the proof is by induction on the degree. On D. Okay, so if D is equal to 1, then F1 is equal to L1, F2 is equal to L2, so we did no extension at all, and the result is tautological. Tau is equal to sigma. Okay, so now we'll do the inductive step. So suppose the claim is true for D less than N. Okay, and then we're going to prove it for D is equal to N. Okay, so in order to do that, so what we do is we let L1 here, this is going to be contained in F1 bar, and L2 in F2 bar. So these are going to be splitting fields, as in the statement of F1 and F2 respectively. And then what we're going to do is we write, we're going to use this isomorphism that we had before. So we're going to let K1 be F1 alpha 1, K2 be F2 alpha 2, where, alpha I is an Li is a root of Fi for I is 1, 2. Okay. So, all right. So what we've done is we've essentially joined a single root here, right? And this setup is something that we've described in a previous video. So we have that. So we had that F1 of alpha 1. This is what we called K1. And what we proved in a previous video that this was isomorphic to this quotient by the minimal polynomial. And we now have this map here, which we also called sigma, right? But this is the map induced on polynomials, and the m, so this is alpha 1, this is m2 of alpha, or m of alpha 2. So we have an induced isomorphism here, right? So this is F2 alpha 2, this is K2. Okay, so this gives us a map. Let me try to do a better dotted arrow. Dot, 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 dot. This gives us an isomorphism between these two fields, and it's induced by the isomorphism between these quotient polynomial rings, which is induced by the polynomial rings. Okay, so this is what we get. Okay, and now this allows us to do induction, right? So we have for I is equal to 1, 2. That this Fi factors, right? So this is G, there's some crap here, times M alpha I x for I is equal to 1, 2. And this thing looks like Gi of x, we can factor out this thing, x here. And so here, So what do I want to do? So let's give this thing a name here, right? And we'll call fi tilde of x. This is going to be gi of x, m alpha I tilde of x, and this thing is going to live in ki of x. So this is for I is equal to 1, 2. So what we're doing is we're taking our polynomial here, and then we're going to peel off a term, and then we're going to look at the junk that's left over and throw that into a new polynomial. And this thing has degree less than, so this thing has degree d minus 1, which is less than n. Okay, so we started with something that was degree, so we supposed it for here. And so in this thing, we're supposing that these two things here, right, these have degree n. Okay? So, all right. So, so Li is the splitting field. Okay, so of fi tilde of x in, so this thing here is in ki of x for I is equal to 1, 2. So we have the same splitting field. It's just different coefficients, and we lowered the degree. Our hypothesis here, so notice that our inductive hypothesis, right, is that suppose the claim is true for degree less than n. It said nothing about what fields we're looking over, right? So we're just saying that, that an isomorphism of fields induces an isomorphism of the splitting fields. It said nothing about which fields, and so we're allowed to extend the field, right? And that's what we're going to do. We're going to extend the field in order to lower the degree of the polynomial and make this whole thing work. All right, and so now the situation is modified. Is now modified where the degrees are lower, and we can apply the inductive hypothesis to show L1 is isomorphic to L2, and what do we call that map in this statement? That's tau, right? So we had this tau, so there existed some tau, okay? Instead of writing this isomorphism, so I'm just going to write this. This was contained in K1 and K2, right? This was like the sigma that we began with, but this contains F1 and F2. And this was sigma here. And this map here was induced by the map on polynomials. So I guess we called this, I don't know, we want to call this like sigma tilde or something, or sigma psi or something, right? So this is the map psi. It's induced by the map on polynomial rings. So this is psi. This thing, the point is that this one came from induction. And then this one here, this little piece here came from just adjoining single roots. And the minimal polynomial behavior. Okay, so that gives us a proof of this result. Now, all right, so we have this extension theorem. So now let me just kind of beef this up. One minor beef up. So I was going to record another video explaining this business, this application of this, but I decided it's best to introduce automorphisms. So let me do that, and just do this in another video.